In this video we are going to talk about feedbacks. Okay, so and we'll talk about positive and negative feedback. I shall start this discussion with the following problem in mind. Suppose I have this circuit where I have an amplifier, say with a gain of G for gain, and suppose that there is another amplifier with gain H. So if this voltage is Vi input to the amplifier, first amplifier, then Vo is the output of this amplifier, of the first amplifier, and then we connect these two amplifiers back to back like this. So the output of the first amplifier goes to the input of the second amplifier, which has a gain of H, and this is the output of the second amplifier. And here we'll have what we call as a summer like this. So it takes two voltages, that we call this as V, one voltage, and this let me call this as V1, this as V2. So then the output will be, here it will be V1 minus V2. So this is just a summer. It takes two voltages as input and gives the difference of that, and this difference is now fed back to the input of the first amplifier, and the output of the first amplifier goes to the input of the second amplifier, and the output of the second amplifier goes to the summer. And since this is connected back to back, so this is feeding back the output of the first amplifier to the input side. So that's why we sometimes, we always call this as a feedback. Okay, and this is nothing but just an amplifier or an attenuator with gain H. This is also an amplifier with gain G. This is another amplifier which has a special name, and the gain is H. Okay, so this is a circuit, and I pose the question to you, which is as follows. Given V1, so V1 is known, so given V1 known, find Vo, the output of this, find this value. Okay, so why this is an interesting problem? This is an interesting problem because this is like a chicken and egg problem. What is that? You see that Vo depends on this Vi, so which is equal to V1 minus V2. Now V1 is known, so that means Vo depends on V2, since V1 known or given, right? So if I tell you the value of V2, you can if I tell you the value of V2, you can immediately find the difference V1 minus V2, and then you can find the value of Vo. Similarly, you see that V2 is dependent on Vo. So V2 depends on VO. So if I tell you the value of VO, you can find the value of V2. But I do not tell you, I tell you neither the value of VO nor the value of V2, and you have to find VO. So to find VO, we need V2, and to find V2 we need VO. So you see, this is a chicken and egg problem. So to find one we need the other, and to find the other we need the one. So that's why this is an interesting problem. This is a small mathematical puzzle. If you like, if you love to solve puzzles, so this is an interesting puzzle. So how can we solve this? So, okay, so this is possible only if we instead of trying to solve VO independent of V2, if we try to solve them together, then we can do it. Then only we can do it. So for that, okay, let us first summarize the functions of all circuit elements that we have here: amplifier, feedback, summer. So let us first write down their functions. So what is the function of, let's start with the summer. The function of summer is like this: to produce Vi, which is equal to V1 minus V2. So it takes two voltages as input and gives Vi as the output. That's the function of the summer. Now let's look at the function of the feedback element maybe. So the function of the feedback element is to take this voltage and multiply it with H, some constant H, and produce V2. So feedback element, this is the function of the feedback element, is to produce V2 as some constant H times VO. And finally the amplifier, it's again an a multiplier, you can say, an amplifier. So its function is to produce VO as Vi times G. Okay, so these are all the relations that we know that we have. We can use all of them together to find VO. We cannot find VO without using all these relations together jointly. So for that, what we have to do? Okay, so let me just use the this equation. Let me rewrite this. VO is equal to Vi times G. So this is nothing but G times Vi, and Vi is nothing but V1 minus V2. Okay, so now I know the value of V1, but V2 is the unknown. So this is one equation. So this is using this and this, and then the function of feedback element tells me that V2 is H VO. So this is equation 2. Once again you see that VO depends on V2, V2 depends on VO. So VO and V2 depends on each other. But we have two equations and two unknowns. So solve together to get the value of V2 and VO together. So that's possible. So what we will have if we do so? So for that, let me do this. Let me in this first equation, which is g v1 minus, so instead of v2 let me substitute this value h vo, then this will become g v1 minus g h vo. So that means let me take the vo together, so I have vo 1 plus this comes to the left side, then I will have gh, and the right side will be gv1. So this implies vu is nothing but gv1 by 1 plus gh, and then I can also compute v2 is nothing but h times vo, h times this value, so this will be gv1 by 1 plus gh. So I can solve vo and v2 both together using these two relations together. Okay, so we have two algebraic equations to solve simultaneously to get two unknowns simultaneously. That's simple. But okay, so this question is answered, but now I'm going to pose a bigger question, and the question is as follows. So let's call this as the bigger question. Let me do it on a new page. Okay, so I have a bigger question which is as follows. The circuit cannot solve equations like human being, like us. Then how does it decide what VO should be? Because the circuit is not a human being, it doesn't have intelligence like us, so it cannot solve equations. So how does it actually decide VO? So at this point this question might seem a bit vague, but I believe as we continue our discussion, this question will be more and more clear to you. Okay, so okay, to answer this question, we have to dig into the topic that I can call dynamics. I can call the system dynamics. Okay, so what is system dynamics? So system dynamics means if I have a system or a part or an part of a circuit or an element of a circuit where there is some input, some voltage, maybe some current, depending on that how the output changes, how it changes with time, how output changes with time depending on the input, and this is what we call as the system dynamics. Okay, so in the previous set what we wrote as the functions of summer, feedback and amplifier, this we can call as static behavior or characteristic, static characteristic. for the summer, amplifier and feedback element. So what it means actually that if I have this amplifier, if I look into this amplifier separately, okay, let me do it here. So let's look at the amplifier only. Okay, so if I give some input, say Vi, so this has again G, so this is Vi, so eventually Vo, eventually after a while, after some time, it will become GVI, G times the input, gain times the input, it eventually, finally will be. But is it that Vo will change instantaneously with Vi? That's the question. So when I write this, Vo is equal to GVI, this is true. I mean, this is eventually true. This is finally true. So the amplifier will adjust its output and to make this happen. So this will happen eventually, and this we call it the static behavior. Okay, but it may be possible that if I say draw this input versus output, let me make a table. Say the input is initially 0 and then it goes up suddenly like a step function. Will the output also be a step function like that, this? Or will it have some delay and eventually go to this final value? Or will it have more delay and will it take more time to reach this final value? Or will it oscillate for some time before settling to the final value? So this is the bigger question, and this is what we call the dynamics. How things changes, how things change, how the output changes depending on the input. And we're not interested only on the final value or eventual value, but we're also interested about the change, this pattern. That's what we call the dynamics. Okay. Now, let us make some assumption about the dynamics of this amplifier. Assumptions. Okay. So, amplifier. Okay. So let us assume that some simple assumptions will make that the rate of change of output. So this is the rate of change of output with respect to time, and this is equal to say GVI minus Vo. So what it means? Okay, one thing is clear that when Vo is equal to GVI, that is eventually, that will happen eventually, finally, after a while. Okay, so when this is true, then you see that this is equal to 0, then ddt of Vo is equal to 0. So that means as soon as the output reaches this value, desired value, gain times the input, the rate of change of the output becomes 0. That means the output settles at that value. Output doesn't change anymore, it stays happily at that value. So it's like, so that means, and if we draw this curve, once again, input, output, So input changes like this, then output was initially 0. So this is 0, so this is then 1. So 0 times g is of course 0, so initially it was 0, but then when it changes it will slowly change and will reach the value of g. So this value will become g, and when this is g, so output, this is VO, this is equal to g, then we'll have g times 1 minus g is equal to 0, implying d dt of v0 equal to 0. So at this point the output won't change anymore and it will stay flat, stay constant. Okay, so this is what we assume about the amplifier. So this is our first assumption about the dynamics of the amplifier. So essentially we say that the amplifier is not an instantaneous device. It doesn't make the output equal to g times input instantaneously. It takes some time, there is a delay, there is a lag, but eventually the output becomes g times input. That's what we say. Okay, so yeah, this is dynamics. Okay, and so what we discussed previously about the amplifier, this was the statics. This is the eventual final behavior. Definitely finally VO will be g times VI. This is consistent with this, but this is how the output will change. So we are looking in more details how things change. Okay, now so this is about the amplifier. Now let's look at say this feedback element H. Now feedback element, what could be its dynamics? So this is our assumption 2. Let's make our life simple. So this is an instantaneous device. So let's go back to the circuit. V2 is equal to HVO. V2 is equal to HVO always. Okay, there is no delay. There is no delay between the change of VO and the change of V2. So if you look at this feedback element H, which takes VO as input and gives V2 as output, this happens instantaneously. So if again draw this input output table, if the input changes like this, the output also changes like this, with some gain definitely. Okay, but this is instantaneous, and I'm making this assumption to make my life simpler. I do not want to start with a complicated problem right at the beginning. So I'm assuming that the feedback element is instantaneous, but the amplifier is not. The amplifier alone is enough to give us a good picture about the system dynamics. Okay, so the feedback element is an instantaneous element. You can think that this is just a potential divider. So this could be just like this. So this is just a potential divider, a piece of resistance. This end is connected to VO, the other end is grounded, and V2 is tapped from here. So this is V2. Okay, so this is an instantaneous device. The moment you change VO, the same moment V2 is changed. That's what we assume. Okay, now let's come to the next circuit element that is left is this summer. So we basically had 3 elements: summer, amplifier, and feedback. So let's make the assumption about the summer. And this is going to be the third assumption. Once again, instantaneous. That means let's look at the circuit. Vi, the output, okay, is the difference between V1 minus V2, and this is always true. So this happens instantaneously. You change V1, suddenly Vi is changed instantaneously, or you change V2, suddenly Vi is changed instantaneously. So there is no complicated dynamics involved in the behavior of the summer. This is again to make our life simpler. Okay, so now we have made all our necessary assumptions to understand the dynamic of this circuit, and therefore we are ready to go back to the question, the bigger question which we posed. How does the circuit decide VO? Because it cannot solve simultaneous equations like human beings. Okay, so let's do that. So for that, I will redraw this circuit once again for ready reference. So I have this amplifier with gain G and another amplifier that is a feedback element with gain H feeding back, and then the summer V1 here plus minus, this is V2, this is VO, this is VI. That's what we have. Okay, so this is this circuit, and now let's see how will this V2 be decided. Okay, so we shall make a table. Okay, so the first column will be time, okay, time samples, and then I will have all these things, V1, then what else, VI, then VO, V1, VI, VO, V2. Okay, so all these things I will have. Right, so time will change from here to here, and these values of V1, VI, they will change from top to bottom. Okay, okay, but before we start, I have to make one more assumption. So one more assumption. So this is about the initial condition. So I assume that initially V1 is equal to 0, Vi is equal to 0, Vo is equal to 0, and V2 is equal to 0. And this assumption is self-consistent. See, if V1 is 0, V2 is 0, then V1 minus V2, that difference. Okay, let me do it here. It says initially at time 0, so I assume V1 equal to 0, and V2 is also assumed to be 0. So that means, see these relationships, the relationships I'm right here, that I must obey. V1 is equal to V1 minus V2. Okay, so Vi then should be equal to 0. This is obeyed. Okay, this is relation 1. And then Vo should be G times Vi. Okay, so then Vo also should be 0, right? And then 3 V2 should be Vo. So now let's see, V2 is 0. Yeah, so all these equations are satisfied. So this is a consistent, self-consistent assumption. I can make this assumption, no problem. Okay, so this is what I assume. Now say after a while this V1 is changed from 0 to the value equal to 1. So what the output will be? Okay, so V1 is 1, so this is changed as a step function like this from 0 to 1. That's how the input is. Okay, Now let me go back to the first page where I had solved this set of equations and arrived at the conclusion that VO should be equal to GV1 by 1 plus GH. Okay, let me rewrite this here. VO, so I'm writing this equation for ready reference, GV1 by 1 plus GH. This is what we got actually by solving all these equations together. Okay, now let's take some values for G, and let's take G equal to 1, H equal to 1, and this is just for ease of calculation, so that and now V1 is changed to 1. Okay, so V1 is also 1, so everything is 1, so that means VO is equal to 1 by 2. That's what we should have eventually. Okay, let's see whether it happens or not. Okay, cool. So now this is 1, great. Then what should VI be? VI is now 1 minus 0. Okay, 1 minus 0 is 1. If so, then VO should be 1 times G. Now G is equal to 1, so this will be again 1. No, it can't be 1. I mean, it can't be 1 instantaneously. I mean, we saw that. Okay, so this is changing like a step function. So here the VI, this should also be like a step function, but here VO cannot be a step function because of the system dynamics that we described. The output of the amplifier takes some time to change, so it cannot go up immediately like this. This is not possible. So it will go up slowly like this. Okay, so this cannot be 1. Okay, so this cannot be 1. So it will go up slowly, and let's assume after a while this becomes 0.1, 0.1. Okay, so let's assume that this is 0.1, right? So this is 0.1. Now this comes through H, so V2 will be 0.1 times H, or again 0.1. And this is an instantaneous device, right? This one is not an instantaneous device, but this is an instantaneous device. So this is 0.1. Okay, cool. So next, okay, so this is next. After that, next again, what we will have, V1 is 1. I keep it constant at the value 1. Now VI is 1 minus V2, that is 0.1, so this will be 0.9. Now this is 0.9. Okay, so now what should happen to VO? Okay, so for that we also need the dynamics of this amplifier, and let's recall this dynamics. It says d dt of the output VO is equal to, now G is 1, so I can write VI minus VO, right? Okay, so VI minus VO. Now VI minus VO, what is that? Now this is 0.9, this is 0.1, so VI minus VO will be, let me make one more column. Okay, here I write VI minus VO. Okay, so VI is 0.9, VO is 0.1, so here this will be 0.8. So now if this is 0.8, so this is positive, that means output should increase. So output will increase and will go to say a new value after a while to 0.2. Now if this is 0.2, then V2 should again be 0.2. Okay. Next what will happen after a while? The V1 is still equal to 1. Now Vi, this is the difference between 1 and 0.8. So this will be 1 and 0.2, so this will be 0.8. And then Vi minus Vo. Now Vi minus Vo will be 0.6. So this is still positive. So this will increase further. And after a while, say I assume that this goes to 0.5. I mean, this will keep increasing, and after a while it will go to 0.5. And then V2 will be 0.5 multiplied by 1 will be 0.5. Okay, if so, then this is again 1. Now this is equal to, okay, so this is nothing but, okay, this is equal to V1 minus V2, right? So V1 minus V2, V2 is 0.5, V1 is 1, so this will be 0.5. Now VU, okay, VU is nothing but Vi, because G is 1, so this will be 0.5. Okay, and then V2, what will happen to V2? Okay, before V2 we need to compute, sorry, we cannot compute it like this. Once again, I made the mistake. I cannot use the static characteristic, I have to use the dynamic characteristic. Okay, so what will happen to this? Let's see. This is 0.5. So when this is 0.5, so 0.5, now Vu is already at 0.5. This is 0.5. So 0.5 minus 0.5, this is equal to 0. So that means the output will not change any further. Okay, so the output will stay at that value. 0.5 cannot change because this derivative is equal to 0, right? So this stays at 0.5, and then V2 is nothing but 1 multiplied by Vu. So this is, okay, this is what I cannot use. So I should use this equation here. T of Vu is Vi minus V. Okay, so this also stays to 0.5, and then if you continue this, you will see that, okay, this is the solution. This is where the circuit will stop adapting its voltages. The amplifier will stop changing its output any further. So finally you see that the VO has become 0.5 or half, which is also given by this set of linear from these equations. By solving these equations, we got VO equal to half, and when we analyze the dynamics of the system, how things change with time, we saw that, okay, fine, eventually the output becomes 0.5. So we are happy in this case because this static analysis gives same result as dynamic analysis. Okay, so the value of VO that we obtained by solving this set of linear equations is same as the value that the circuit will eventually land up to by slowly modifying the VO from one value to the other. And this is how actually the circuit decides how the value of the output should be changed, because it cannot solve a system of equations, it cannot solve equations like us. So this is how slowly it modifies depending on the dynamics of the components, and eventually lands up to some value. Okay, now in this case we are happy because static analysis and the dynamic analysis give same result, but this is not always true. This is not true for all situations. Let us see such a situation. I would rather say half of the times this is true and half of the time this is not true, and we will see one example from the other half of the times. Okay, so what I will do, I will still use the same circuit. So G amplifier, H feedback element. Here we have this differentiate, whatever you call it, summer, subtractor, I don't know. I don't care much in this video. So this is V1, this is VI, this is V2, this is VO. That's what we had. Okay, and here this was the relationship we had from static analysis. This says VU is equal to G V1 by 1 plus GH. For simplicity, once again we will take G equals 1, H equals 1, and let's also take V1 is equal to 1. So everything is 1. Okay, one thing will change. Here I'll take H equal to minus 1. Okay, so H is equal to minus 1. In the previous example, everything was 1. I'm changing this H to be equal to minus 1. You see? Okay. So if so, then let me put the values. Then VO is equal to G is 1 times 1 divided by 1, and then plus 1 times minus 1. And then this is undefined. This is 1 by 0. This is undefined. Okay, so in such a situation, we cannot compute VO like this. This is difficult. Okay, let me make our life bit more simpler. Let me just choose H to be equal to minus 2 and G equal to 1 as before, and say V1 that is this input is equal to 1. So what do we have then? VO is GV1 divided by 1 plus GH. That's what we have from our static analysis here. Okay, so let's put the values. So I will have then 1 times 1 is 1 divided by here 1, but now minus 2. Okay, so then this will become minus 1, right? Okay, So this is what the static analysis tells us, that VO should be equal to -1. Now let's look at the dynamics of this system. For that, to understand that, we'll again make a table as before. So let us have time first, definitely some time, and then we have V1. Now V1 is always equal to 1, so this is equal to 1 always. Then after V1 we have Vi, so let's write Vi, then Vu. Okay, Vu, for that let's first take this Vu minus Vi, and then what happens to Vu we'll see. And then, okay, let me draw these lines. After VU we have V2, and then, okay, so that's all we need. Okay, and the equations that we know are V1 is always 1. I mean, after the step change, we'll always keep it equal to 1. So after the first beginning, let's not write it then. So initially this is 0, and we start with the situation with everything equal to 0 initially. So you see that this is a self-consistent situation. This is 0, this is 0, their difference is 0, that multiplied by 1 is 0, that multiplied by -2 is 0. So everything is 0. So this is a self-consistent situation, no problem. Okay. So and after that, V1 becomes 1, and it stays to be 1 always. Okay. So this is a step change. And then Vi. So about Vi, we know that Vi is V1 minus V2. Okay. Okay. And then VO, about VO we know that the rate of change of VO is proportional to this value, VO minus VI, VO minus VI. That's what we have from this dynamics that we discussed. G is 1, so the rate of change of the output is VI minus, oh sorry, this is VI minus VO. Okay, then let me also take this as VI minus VO. I minus O. Right, VI minus VO. And then V2 we know is H is -2, so this is equal to -2 VO. Okay, so we start with all zeros, and then V1 becomes suddenly 1. If so, now Vi, what it should be? This is V1 minus V2, so 1, V2 is now 0, so 1 minus 0, so 1 minus 0 is equal to 1. And then Vi minus VO, so this is 1 minus 0 is equal to 1. So then what should happen to VO? So this is, see, Vi minus VO, this is 1. So that means this derivative is positive, so VO should go up, should increase. Say it increases to a value of 0.1 after a while. Let's assume that that's what happens. If so, then what is V2? V2 is nothing but -2 VO. So this is minus 0.2. Okay, if so, now let's come to the next step. So next step, V1 stays at 1. Now Vi, this is equal to 1, V1 is 1, 1 minus V2, so this is 1 minus V2, I mean after the starting. Okay, let's not write it. So this is 1 minus V2, So 1 minus V2 is now minus 0.2, so plus 0.2, this is 1.2. okay, so this is 1.2. Now here we'll have Vi, which is 1.2, minus VO. VO is 0.1, so minus 0.1, so this is equal to 1.1. okay, so now you see that this value is increased, so therefore the rate of change, this derivative, should increase. So it will increase further, and maybe it will increase more than the previous step, and will go to possibly 0.21, I guess, so after a while. And if so, then this V2, this will become minus 2 times this, so this will become minus 0.42. okay, now let's come back again to the next step. Here you see that this is 1 constant, so Vi will be 1 minus V2, that means plus 0.42 plus 0.42, this is 1.42. So this will be 1.42 minus this value V0, which is 0.21. So this will become something like, if my calculations are correct, this will become 1.21. Then if this is 1.21, see, this is even larger than this. This was 1.1, now this is even. So V output should increase further and should increase more. Okay, so it will keep increasing, and after a sufficient while, this may go to maybe 1. After a sufficient amount of time, this may go to 1. Okay, and if so, then V2 will be minus 2. And then next step, this is still 1, then we have 1 minus 2, this will become 3. Now you see that this is 3 minus VU, which is 1, so this is equal to 2. So this is even larger, so this will grow even further, maybe it will go to 3, 4 or something, and it will keep increasing this way. If we continue this table, we will see that VO increases continuously like this. Okay, so this table never ends. So this is a never ending table. Or if you are a good programmer in your language, we are running into an infinite loop. So this VO is going to keep increasing forever and ever and ever, and then it's not going to stop. And then this static analysis, which says that the output should be equal to -1, is not true. This is not true. So we see that the static analysis in this case is not correct, and it's not consistent with the dynamics of the system. So because in a previous slide, we when h was +1, we were happy that the static analysis and the dynamic analysis gave same result, but in this case, when h is -2, you see that these two are not giving same result. Okay, and this situation we shall call it as a positive feedback situation. Why? Because h is equal to, in this case, -2, right? And then this summer is actually subtracting the minus 2 times VO, so which essentially means it's adding V1 and 2 times VO. So it's actually doing a positive addition of this output with this V1. So that's why we call it a positive feedback. Whereas in the previous diagram where H was equal to 1 plus 1, then this minus and this plus, they resulted into a proper subtraction. Okay. So this minus was minus, really minus, negative. So that's why we call this situation as a negative feedback situation. And in this situation we saw that the static analysis and the dynamic analysis gave same result. The system eventually landed up to this value of 0.5 and got stabilized. Okay, so the value finally went to 0.5 and stabilized. So this situation we called a stable situation, stable system, which was due to this negative feedback. And now this is an unstable situation. See, the output is increasing continuously, stopping never. And this is an unstable system. Okay, so in this video, let me summarize. We started with a simple circuit like this, where we had 2 amplifiers, one feeding back to the other, and we said find the VO output given the input, and we said that this is a chicken and egg problem, but then we solved it by solving a set of equations and that we called as the static analysis of the system. Then we moved on to the discussion on the bigger question that the system cannot or a circuit cannot solve equations, so how does it change the output? And that led us to the discussion of system dynamics, and we used some simple example for this amplifier, and we came up to 2 situations. One is of positive feedback, where we saw that the system becomes unstable and the static analysis doesn't give correct result. Whereas in the other situation, if you recall, we saw that the feedback was negative and the system is stable. It finally lands to a value which was also consistent in this example with the static analysis.